Okay, in this video, lesson 3.2, we're finally beginning those notes, and there'll probably be 2 videos left in this lesson. We're going to talk about enthalpy and calorimetry. I want to warn you, I'm adding 2 videos that I made last year, so I don't know, the ones from last year, they might look a little different, or I might sound a little different because I'm editing ones that I did last year. Okay, so in the last video we said that enthalpy was equal to the heat of transferred at constant pressure. The heat transferred into or out of a system at constant pressure, and we went through some equations to show this. This little p means constant outside pressure on the system. Now what we're going to think about are reactions. So let's just write down a sample reaction. So I've written down a sample reaction, and this reaction is endothermic. So that means heat is necessary to go into, and actually before I say that, we're going to think of the system as being the reaction. So whatever is happening in the box where the reaction is taking place, and this particular reaction has sodium bicarbonate, baking soda, being mixed with hydrochloric acid. We're making sodium chloride, carbon dioxide, and water vapor. And so what's happening in a box, and the reaction is the system. We can put it in a box just to define that, but the reaction is the system, and it is endothermic. So if we were to do this in the lab, and I don't think we did it last year, if you had it in a little crucible and you were holding it in your hands, here are your 5 fingers, your hands would actually feel cold because heat would be leaving your hands to go into this crucible. This has to take in heat from the surroundings, from the surrounding air or your hands or the crucible, because it's endothermic, so I'll write that there. So if it's endothermic, that means that the internal energy of the products, which are over here, has to be greater than the internal energy of the reactants, because if you, well, I'll say it now if I'd never said it last year, but I think we did. Molecules hold energy in their bonds. You need energy to break bonds, and when bonds are formed, it's released. There's energy, chemical energy held in bonds, in molecules. So we're going to look at this picture, this graphic to help. Not that. Oopsies. This one. Nope, not that. Bear with me. Okay, so in this picture, this is a diagram of the energy of the products and the reactants. And as you can see, this is your y-axis is your energy scale. So you can see the energy of the products is higher, it's a higher point on the y-axis, than the energy of your reactants. This is a potential energy diagram for a reaction. And it's for an endothermic reaction because the energy of our products is greater than what the energy in the bonds that we started with. So if we were to calculate delta H from our diagram, and we knew the values over here of this on this y-axis for the products, we knew the energy value here and the energy value here. This would be final, or P for products. This is R for reactants. We could calculate our delta E. It would be equal to the energy of our products minus the energy of the reactants that we started with. That would be the change in the energy. If the energy of the products are greater, then it's going to be endothermic. It's going to end up being a positive number, which it is in this case. If this diagram was flipped, I'll try to do that. Of course, it doesn't want me to. If we were talking about a different reaction, totally different reaction, that happened to be exothermic, it would look like this. You'd have your reactants up here, and your products would have an internal energy that was less because they would have lost energy. This is, and your change in enthalpy would be in between, and it would be a negative number. This is for an exothermic reaction. Okay. And just to tie this to the notes, when I'm talking about enthalpy at constant pressure, this is all happening at constant pressure because we're underneath the Earth's atmosphere. We're assuming that we're under constant pressure. So now we're going to talk about how do we calculate the enthalpy of a reaction, because it's very important to figure out, is a reaction exothermic or endothermic? And if it's exothermic, how exothermic? How much energy is being released? And if we need energy to make it happen, if it's endo, how much do we need? So we're going to talk about how we calculate now in numbers this delta H. So, how can we calculate changes in enthalpy? There are 4 ways we're going to talk about. Stoichiometry, which you already are experts at. Calorimetry, which we're going to talk about in this video. Hess's equation, which is a flippy thing. Oh, that says equation. And something we're going to call the Big Mama equation, only because it shows up that way in the notes that I'm using, which we'll talk about at the end of this video. Okay, so we're going to use stoichiometry and enthalpy to answer this question. It says, consider the combustion of propane, and here we have propane, C3H8, that is propane, these should be subscripts, plus 5 O2 molecules makes 3 molecules of carbon dioxide and 4 molecules of water, or moles. And the enthalpy of this reaction is negative 2,221 kilojoules. And the fact that it's negative tells us that it is exothermic. So since it's exothermic, that means when these products come together and bump together, they release energy, which means we can actually write the energy, if we wanted to, as another product because it's being created, it's being released. And so it says, assume all the heat comes from the combustion of the propane. Calculate delta H, in which 5 grams of propane, so you know I like to write my grams over my equation, is burned in excess oxygen. And all the word excess means is that you have enough oxygen to make all the propane burn. So don't get too bent out of shape out of that. Oh, and we have the answer here. We're going to Okay, we've eliminated the answer now, so we're looking what happens if 5 grams of propane is burned in excess oxygen. So what this equation tells you, or what this enthalpy tells you, come back, right here, this is the enthalpy for 1 mole of propane. Because this is the enthalpy of this reaction, so it's for 1 mole of propane. So we're going to use stoichiometry. Let's go ahead and make this a little bit smaller. So now I have 5 grams of propane, and I'm going to multiply that by, I'm going to turn that into moles. So there are 44 moles of propane, or 44, oh, stop it. There are 44 grams of propane in 1 mole of propane. And then I just told myself that found out that the enthalpy, the change in enthalpy for 1 mole of propane was minus 2,221. So for 1 mole of propane combusting, I create minus 2,221 kilojoules. And so then I'm just going to use stoichiometry to figure this out. My units cancel, and my answer is minus 252 kilojoules of energy are released when we burn only 5 grams of propane. Woohoo! Okay, the enthalpy for the formation of sodium oxide is shown below, and it's negative 828 kilojoules. What is the amount of heat released when 1 mole of Na2O is formed? Only 1. So this was for the formation of 2 moles of sodium oxide. And so if 1 mole is formed, all we have to use is stoichiometry again. If we have 1 mole of Na2O, and we know that for every 2 moles that are formed in this reaction, minus 828 kilojoules are released, then minus 414 kilojoules are created for 1 mole. Okay, here we have the enthalpy, or heat of reaction, for the decomposition of iron oxide. And remember, decomposition, a word that means you go from one thing and it breaks down into its parts. And the important thing in this question is, well, they're asking you what is the enthalpy change for this reaction down here. Now we know that for 6 moles of iron oxide, they decompose into 4 Fe3O4s plus 1 mole of oxygen gas, and that is endothermic and requires 472 kilojoules of energy. Let's look at this reaction. It is 4 iron 3O4s plus 1 mole of oxygen, making 6 iron oxide. So it is the opposite it is the synthesis of 6 moles of iron oxide as opposed to the decomposition. So if you reverse a reaction, then you reverse the heat of the reaction. So in this case, for this reaction, the heat of reaction would be minus 472 kilojoules. Because in the earlier case, up on top, if this is endothermic, that means you can think of the heat as being a reactant. 472 kilojoules were required, and so if you reverse it, then those 472 kilojoules are going to be released. So we're going to stop here for this set of videos, and I might cover a little bit more in class, but this is the end for this day.